Welcome! Today we embark on an adventure to understand Earth's atmosphere, this vital envelope that protects us and influences our daily lives, including the flights of aircraft. This invisible shield is more than just the air we breathe. It's a complex system, full of mystery and wonder, which plays a significant role in everything from the weather we experience to the flights we take. Meteorology, the study of the atmosphere, is crucial for aviation. Although pilots cannot control the weather, understanding it helps them anticipate and manage meteorological difficulties. Our atmosphere is a complex mix of gases, predominantly nitrogen and oxygen, which together make up about 99% of the total. Nitrogen, the most abundant gas, accounts for about 78%, while oxygen contributes just under 21%. This duo plays a vital role in sustaining life on Earth, with oxygen being essential for most forms of life, and nitrogen playing a key role in the growth of plants. Next comes argon, a noble gas that makes up slightly less than 1% of the Earth's atmosphere. Although argon doesn't participate in many chemical reactions, it's vital for certain industrial processes and is used extensively in lighting and welding. Now let's talk about the atmospheric underdogs, the trace gases. These include carbon dioxide, neon, helium, methane, krypton, hydrogen, and ozone, each making up less than 0.1% of the atmosphere. Despite their minuscule proportions, these gases have significant roles. For instance, carbon dioxide, though present in small amounts, is a key player in regulating the Earth's temperature. But the atmosphere isn't just a cocktail of gases. It also contains water vapor, which varies in concentration but can make up to about 4% of the atmosphere. Water vapor is responsible for weather phenomena, playing a crucial role in cloud formation and precipitation. And let's not forget the atmospheric solids, dust and other particulates. These tiny particles can originate from various sources like volcanoes, dust storms, forest fires, or even man-made pollution. They can affect weather and climate, acting as surfaces for water condensation, influencing cloud formation, and impacting visibility. Lastly, our atmosphere is a literal air zoo, hosting a variety of microorganisms. These airborne bacteria, fungi, and viruses, though not typically considered when discussing the atmosphere, can impact weather, cloud formation, and even human health. So, there you have it. The Earth's atmosphere is not just a blanket of air. It's a dynamic, bustling ecosystem with a complex composition that directly influences our weather, climate, and life as we know it. Besides gases, the atmosphere contains water vapor, dust, and microorganisms, which can variably affect weather conditions. The atmosphere is not uniform. Its composition and temperature vary as we move away from Earth's surface, extending up to about 800 kilometers in height. The vertical structure of the atmosphere divides it into 5 principal layers, each with unique characteristics. Firstly, we have the troposphere, the layer closest to the Earth's surface, extending about 7 to 20 kilometers upwards. This is the layer where we live and where most weather phenomena occur. It's characterized by a decrease in temperature with height and contains about 80% of the total mass of the atmosphere. Above the troposphere, we find the stratosphere, extending up to about 50 kilometers. This layer is home to the ozone layer, which absorbs and scatters the solar ultraviolet radiation. Unlike the troposphere, the temperature in the stratosphere increases with height. Next up is the mesosphere, stretching up to 85 kilometers. Here, temperature again decreases with height. This layer is where most meteors burn up upon atmospheric entrance, creating meteor showers. Above the mesosphere, we have the thermosphere, reaching up to 600 kilometers. This is where the atmosphere starts to thin out, and temperature increases with height. The northern and southern lights occur in this layer due to the interaction of solar particles with gases. Lastly, we reach the exosphere, the outermost layer of our atmosphere. This extends from the top of the thermosphere up to about 800 kilometers. Here, the atmosphere gradually fades into the vacuum of space. Each of these layers plays a crucial role in our planet's climate, weather patterns, and protection from harmful solar radiation. They also significantly impact aviation, from flight paths to communication systems. We will discuss the layers of the atmosphere, from the troposphere, where most weather phenomena occur, to the exosphere, where the atmosphere thins out into space. For standardization, aviation uses the International Standard Atmosphere Model, which assumes average values for temperature, pressure, and density at different altitudes. These standards are essential for calibrating flight instruments. Imagine you're a pilot soaring through the skies. The cockpit is your office and the instruments are your tools. But how do you make sense of all that data? How do you know if the readings are accurate? That's where the International Standard Atmosphere, or ISA, comes into play. The ISA is a model that represents the average atmospheric conditions throughout the year at all altitudes. This model is based on observations and measurements taken worldwide, and it provides a standard reference for temperature, pressure, and density at different heights above sea level. Why is this important? Well, think about it. Planes fly at various altitudes, and each altitude has different atmospheric conditions. The ISA helps pilots understand what they can expect at each height, allowing them to plan their flights more accurately and efficiently. The ISA also plays a crucial role in the design and testing of aircraft. Engineers use these standardized conditions to ensure that all aircraft can perform optimally, regardless of where or when they are flying. Now, let's talk numbers. According to the ISA, at sea level, the standard temperature is 15 degrees Celsius, the pressure is 1,013.25 millibars, and the density is 1.225 kilograms per cubic meter. As we ascend, these values decrease. For example, at 10,000 meters, the standard temperature drops to minus 56.5 degrees Celsius. But remember, these are just averages. Real-world conditions can and do vary, which is why pilots also need to understand weather and atmospheric science. In a nutshell, the International Standard Atmosphere is a key tool in aviation. It provides a common reference point, ensuring that whether you're a pilot in New York or a flight engineer in Tokyo, you're all speaking the same language. Understanding the atmosphere is vital for aviators, helping them to safely navigate through various meteorological challenges. Stay tuned to explore each layer of this fascinating gaseous envelope in more detail. Understanding the atmosphere is vital for aviators, helping them to safely navigate through various meteorological challenges. We've journeyed from the ground level, composed of a mix of gases, to the varying layers extending up to 800 kilometers. We've also touched on the International Standard Atmosphere, a model that ensures standardization in aviation. Each aspect contributes to a clearer understanding of our atmosphere, a complex yet fascinating gaseous envelope. Stay tuned to explore each layer of this fascinating gaseous envelope in more detail. Don't forget to subscribe for more captivating information on weather and aviation. Our journey into the skies is just beginning, and there's so much more to explore. From the layers of the atmosphere to the intricacies of flight, together we'll soar. See you soon.